Hello everybody, welcome back to our channel, chemistry again. Okay. Previous week we talked about ionic bonds. Now we will spend a few weeks to talk about covalent bond. It's a big topic, big foundation again. So what's a covalent bond? Probably you learned it in the junior form. When in the IBDP level, we want to share it with one statement. Okay, covalent bond is the electrostatic attraction between the positively charged nucleus with whom? With the shared electron. So the two positive nucleus are attracted by the bonding electron, so the three things are drawn together. Okay, this is formed as a result of electron sharing. Oh, very funny way to bond to atom. So even though a covalent bond is formed by electron attraction between a shared pair of electrons and the positively charged nuclei at the two sides. So the two positively charged nuclei attract each other, and we have the octet rule. Okay, this is a tendency of atom to gain a valence shell with a total of 8 electrons. Of course, hydrogen is 2 electrons. Okay, so the number in the lower right corner, not the upper right corner. Lower right corner is the number of elements bonded in the molecule. So if A and BM, it means the Na and M atom B bond together. So be careful. Lower right corner, look for it. So be careful when you are An and Na, they are different. Okay, Am means that they are bonded. Na means they are not bonded. They are separated. Be careful. And when sometimes we want to say clearly what kind of bonding do they have, how many bond do they have? So we have a stroke for it. Okay, one stroke is a single bond, one pair of electrons shared. Double stroke, double bond, two pair of electrons shared. Three stroke, triple bond. Okay. In general, a triple bond has stronger because there are more electron being bonded. And then the double single bond is the weakest, of course, okay? Because if you look at it, triple bond, you have 6 electron bonding together. Wow, the electrostatic attraction is strong between the nuclear and the electron, the 6 electrons. But the single bond, just 2 electrons. Okay? So it's weaker. So you can say and triple bond is stronger than O2's O double bond, and then also stronger than FF because they're single bond. So we have a neowise structure to represent electron because we have sharing of electron. Right? We have to distinguish where the cis electron come from the which bonded atom. So we have the dot and cross symbol. Both the dot and cross symbols represent electron, but they represent electron from different elements, different from the left or from the right. Okay. For the single bond, you can write it this way. Dot and cross together, one from one bond and the other from the other atom. Okay. For the double bond, 2 cross and 2 dot. Okay, 2 electron from one atom and 2 electron from the other atom. They form a double bond. And of course, sometimes maybe this kind of a single bond is all the electrons are from one atom. We call it dative bond. Okay, so either 2 cross or 2 dot. Okay, so this is the good way to represent different kind of bond, dative or not dative. Okay, number of electron share, single bond, double bond, or triple bond. Okay, remember you need to draw all the lone pair of electrons, even the not bonded lone pairs. Okay, all the outermost shell electron, you have to draw it out. Okay, example like this for HCOOH. Okay, and carboxylic acid. Okay, do single bond, double bond, single bond, single bond. Okay, and then you have to draw it out. Okay, single bond, double bond, single bond, and then you have to count. Okay, oxygen and oxygen still have some lone pairs, so you have to draw them out. Okay? And this is a very important, okay, because IBDP require you to draw it out and recognize. Okay, the trick is that alternate dot and cross for labeling atoms. Okay, so we use the cross to represent hydrogen, then dot is carbon, and then O is cross, and then dot. This is dot, and then this is cross. Make sure no confusion. And the number of covalent bonds, yes, just count it out. Okay, one covalent bond is one extra electron in the bond atom. They share one out, and then they can take both the electron as themselves as an electron. Okay, single, double, and triple bond involve 1, 2, and 3 share pair of electron respectively. One bond, one bond pair of electron. So 2 bonding electrons. Remember, just counting games. Okay, one pair is 2. Everyone knows it, right? So count as 2 in the log octet rules too. So they can increase the number of electrons when they counting the octet rule by covalent bonds. So number of bonding electron is number of covalent bonds times 2. And valence electron is outer electron which is not bonded. Not bonded is the valence electron. Okay? If two valence electrons, we call it a lone pair. Okay? They can be single sometimes. Okay? We call it a radical. We'll learn it later. Okay? And number of a lone pair of electrons is the number of valence electrons divided by 2. It's the opposite, right? Number of electrons is divided by 2 is number of pair, right? So in general, H2N, okay, means that A has an N covalent bond with a hydrogen atom. For example, H3C and H2. Wow, so 3 bond, 2 bond, 1 bond. So actually 6 covalent bond. So 12 bonding electrons. So sometimes be careful, there's some hidden bond, not written. Okay. So complete octet would normally the bonded atom should have a completely filled shell. For N equals 1 hydrogen, just one example. So 2 electrons again. For the other 2 and 3 are 8 electrons. For N equals 4 is more complicated, we'll talk about it later. Okay. So number of required electron towards the complete octet rule is the number of covalent bonds. Okay. So if they have just, for example, hydrogen just has 1 electron, so it lacks 1 electron for octet rule. So it needs 1 covalent bond. For nitrogen, the structure is 2, 5, just 5 outermost shell electron. So we need 3 more to be octet rules, right? So it lacks 3 electron. So it needs 3 covalent bonds. You need to look at the periodic table, look at different elements, and think about this concept, and you will get used to it quickly. Okay, trust me, you are smart. Okay. There are exceptions for octet rules. So for example, BH3 and BCl3 is still stable. Okay, they are stable. We'll use them later. Okay, they only have for the boron only have a 5 outermost shell electron. So 6 outermost shell electron, lack 2 electron, but it's still stable by itself. So the molecules are given in the exam paper may have hidden bonds. Okay, so be careful. Yes, okay, be careful because they have some symbol, maybe CH4. Okay, they just write out, but actually they have 4 bonds between the C and the H. Okay, so you have to draw all the full structural formula to find out number of bond. Okay, length and strength of bond we have talked about it, but now we go from the strength to the length. Okay, remember if the bonding is stronger, the 2 nuclei will be pulled closer together, right? So the bonding will be shorter. So the stronger the bond, the shorter the bond. Okay, so remember the story, remember the reasoning behind, and you figure it out easily. And actually in the exam, you need to explain it. Okay. So concept is important, not just remember the facts. Okay. So but the bond strength, triple bond is stronger than double bond is stronger than single bond. So for the bond length, triple bond is shorter than double bond is shorter than single bond. Right? For the hydrogen carbon, you can say alkane. Alkane also only has a single bond. Alkane has a double bond. Alkane has a triple bond. So alkane is closest for the carbon, and alkane is far away a little bit. Alkane is the farthest away. So we just look at the single, double, and triple bond. You understand whether they have a different strength and different bond length. Then dative covalent bond we have talked about it. What is dative covalent bond? It means that the dative bond is shared by 1 electron. Both the 2 electrons are shared by 1 atom. Okay. So there must be 2 atoms. One atom has a lone pair, and the other has a vacancy of 2 electrons, so they meet. Okay. Just like this. Okay. For these 2, they have a perfect match for dative bond because this electron has a lone pair, and this is one. And then this atom only has 6 electrons and has a vacancy of 2 electrons. Wow, perfect match. Okay, so the X proton length is lone pair to Y. Okay, then both are happy. Both have the octet number fulfilled. Excellent. So it's a dative bond. Okay, both electrons come from one species. So one species can be donated and one species has space, right? So one species has a lone pair and the other species has a 2 electron vacancy. Okay. Match. Okay. Typical example is like this. Okay, for oxygen. Okay, in water it has 2 lone pairs, so it is ready to donate its electron to someone to form the dative bond. For NH3 also has a lone pair ready to donate. Okay, and then who will receive it? Hydrogen ion. Hydrogen ion has outermost shell electron 0. Okay, so it needs 2 more. It has a vacancy of 2 electrons, so it's a perfect pace to match. And then when they match, we have the arrow here. When they match, we have the arrow here. So sometimes when you draw, remember just bear in mind, okay, whether it is an arrow or it's not, it's just a stroke. Okay, an arrow is a dative one. You got it. Well done. It is a famous example. We talk about it later when you talk about acid base, some advanced theory of acid base. So NH3 and BF3, okay, wow, excellent match. Okay, nitrogen has a lone pair, boron has a vacancy of 2 electrons, perfect match, so they can form a dative bond like this. This is an excellent example for some advanced concept of acid base. Okay, and then lone pair bond together. And sometimes the events the Y can replace the X before H and X are bonded, but Y comes, okay, Y is more reactive, so Y can replace X, forming the bond with the hydrogen, and the X we take out all the dative and become a negative. So the reaction is like this. And of course, sometimes it's a very different. The dative bond may form within the molecules. For example, look at CO2, okay, carbon monoxide. So in the carbon monoxide, the oxygen has a lone pair, right? And the carbon has 2 vacancies. So the oxygen will donate its lone pair to the carbon within the molecule, so it becomes like this. Okay, so the oxygen donate 1 electron to carbon, so it's become positive. Carbon receive an electron from oxygen, become negative, but overall it's still neutral, so it's a C triple bond. Okay, but one is a dative bond. CS is the same. CS is a phi bond, triple bond, but one is a dative bond. So A forms a dative bond to H plus. Okay, effectively, okay, a proton is added to A, right? So we can say A is a protonator. We can use the term protonator. And then we have the theory called VS EPR theory, valence shell electron pair repulsion theory. It's a fairly easy theory. Electron repel electron. Yes, I know it. Okay, so the electron on the bond pair and the lone pair wants to be separated as far as possible in a 3-dimensional way, not 2-dimensional way. Be careful. Okay, so we got a VSEPR or repulsion. The electron pairs in the same valence, okay, shall repel each other as spread out as possible. Okay, so we have to count how many electrons there. But we call it electron domain. Okay, electron position. Lone pair and bond pair both count as 1. Okay, double bond is still count 1. Okay, so number of electron domain is number of electron position. But be careful, double bond, triple bond only count at 1 position because they have the same position happening. Right? So first find the central element, and then cast the number of bond position for it, and then they study whether it is lone pair or not. If it is lone pair will repel the other more because it is not attracted by 2 nucleus. Okay, just attracted by 1. Okay. Okay, the shape and the bond angles of a species depends on the number of electrons. We have some discussion afterward. Very fancy theory. Sometimes it's octet rule, sometimes it's beyond octet rule. Okay, to simplify, we don't use the Lewis structure, too complicated. Okay? But they're more just use the dog. It's excellent. Okay, IBDP requirement. Okay, we need to predict the electron domain geometry. Okay, and the molecular geometry with the same what is this trigonal, pyramid, or whatever you say. Okay, and then predict how a long bonding pairs, okay, and multiple bonds affects the bond angles, larger or smaller than the normal one. What's the normal one? We'll talk about it now. Okay. So for example, for 2 electron domains, okay, fairly easy for BAB, FBEF. Remember this one means a low lone pair, okay? So it's a straight line. Whether it's double bond or single bond, still a straight line. Even triple bond is still a straight line. If low lone pair, okay, be careful, okay. For complex species, okay, you can also have a linear scale, okay. All the elements except at the 2 ends must have low lone pair. This is the golden rules, okay. If you want to have a straight line thing, okay, at the 2 ends they can have lone pair, but in the middle, low lone pair. All must be bonded, okay. Then they can have a straight line like this, okay. C2H2 is a straight line, okay. We got it. And also for this nitrogen monoxide N2O, okay, always appear, and this shape is not the N minus N plus O. Be careful. It's linear. So 3 electron domain, it is equilateral triangle for the outer 3 parts, okay. So 120 degree, okay, pins in principle. It can be a little bit smaller. For the other one, if one of them is a lone pair, remember lone pair, but the theorem will repel the other bond pair more, so the angle will decrease a little bit. But whether it's 119 or 117, you don't need to remember. It just says something close to 120, but a little bit lower than it. 119, 117 is excellent. Okay. So this is important. When you look at this SO2, don't think that it's linear structure because it's a lone pair. So it's a 3-electron domain. For this one, it's a 4-electron domain. Maybe they are all bond pair, everyone, okay, no problem. It is a 3-dimensional way because it's a pyramid, 3-dimensional. So all of them will be 109.5 degrees. You need to remember this one is the symmetric one, tetrahedric shape. Okay, it's 109.5 degrees. Okay, when you draw it, okay, you can draw a linear graph, of course, a plane graph, 2D graph, 2D graph. Okay, but actually it is a 3-dimensional. How to draw it? The 2-stroke is on the plane. Okay, and the broken line is behind the plane. And the little triangle out is outside the plane, so it's a 3-dimensional drawing. You need to learn it, okay? On the plane is 2 hydrogen, behind the plane is H, broken line, in front of the plane is H, little triangle one. Be careful about this drawing. It's excellent. You use it 1,000 times. So remember, you know how to draw the tetrahedral shape. Draw a 3-dimensional shape on the 2-dimensional paper. This is some skill, okay? Broken line and little triangle. Remember, broken line is behind, little triangle is in front. Okay? Of course, maybe it has a electron lone pair, okay? But it's still a 4-electron domain. But remember, the lone pair is invisible. We can't see the lone pair. We can just see NHHH. Okay. So what is this shape? Okay, you just see the base is triangle shape again in this pyramid. So we call it trigonal pyramidal shape. Okay, not tetrahedral. Because we can't see the lone pair. What we see is a triangle base and the pyramid shape, so we call it trigonal pyramid shape. Okay. Even if you have 2 lone pair, okay. Wow, what will you see? Just a V shape, okay. Right? Just a V shape, okay. And for this one, to that one, remember the lone pair will repel the other bond pair more, so the angle decreases from 109.5 to 107. And even this 104.5. Okay. In some cases, just say it's smaller than 109.5. Just say 107, 108 to a mile simply estimation is excellent. Okay. Smaller than 109.5 is excellent. You don't need to remember 107 or 104.5. Okay. It is, you can Google it, you see that way. For complicated species around a different atom to have different electron geometry, pay attention to which atom. That's the question asked about. With them a lot of atoms. Okay. Look at which one they are talking about. And electronegativity. Electronegativity is the ability, we've talked about it before, of the atom to attract a bonding pair of electrons. The stronger the electronegativity of the atom, it will pull the electron towards itself stronger. So we call it electronegativity. And in theory, you use a positive number. So the lowest electronegativity one is 0.7, stronger is 4.0. Okay. We can decide the bonding by comparing that. We'll talk about it later. Also in the triangle, formalism. Okay. Okay. Type of bonding with their difference in electronegativity is very small, and then it's the pure covalent. It's a little bit bigger. It's a polar, fairly big, then become ionic. For example, for the bond polarity, okay, for if they have the same, nearly the same electronegativity, then the electron will be at the middle, so they are non-polar. If X has a higher electronegativity, it attracts the electron cloud more here on the left-hand side. The left-hand side become a delta minus, and the positive Y become a delta plus. And we have to draw an arrow with a cross at the back to show that it is showing the polarity, okay, not native bond, okay. And then the arrow, so the arrowhead is the point where is delta minus. So remember this polarity arrow is from delta plus to delta minus. And how can I know whether it is a strong polar or not polar? Look at here the rules. Okay, because okay, electronegativity is higher where larger group and smaller period. Yeah, it's the largest. Okay. So if this is 2 bond, wow, largest difference between them. Here medium, this is a lithium. Okay, closer is a lithium, of course. Okay, so you can understand whether they will form an ionic bond, covalent bond, or very polar covalent bond. and polar and non-polar molecules. So sometimes it's easy, right? If this is a linear, more electronegative one will have negative, yeah, more less will be positive. It's easy to understand, but in if more complicated system, you have to think about symmetry. If it has a symmetry, then overall maybe you can't see the polarity. For example, linear, trigonal, tetrahedral. If both are symmetric, okay, all the outside are delta minus, so the whole outside is delta minus, right? Remember the polarity is two ends, right? So at the surface you can see no difference, so they are non-polar. So even they have different electronegativity, draw them out. If they are in symmetry, non-polar still. But if one of them change to C, change one to another element with different electronegativity, so the polarity, the symmetry breaks. So it depends on which one is stronger. Okay, so you can have a polar molecules overall. So be careful. Symmetry for the V shape is always polar because it is not symmetric. It has a lone pair, lone pair, lone pair. So if it has a lone pair, no need to think about it. Always be polar. Thank you for going through with me. Okay, we have lots of things learn. Okay, face the first. 2-domain system, 3-domain, 4-domain is easy already. Later we'll learn 5, 6-domain system, even 7. So get used to it. Okay. See you next week. Okay. If you like our share, remember subscribe and share our channel with others. See you. Bye.